Let us continue oxygen family. In the oxygen family, we will take hydrates of oxygen family. We will take in the hydrates of oxygen family: water, H2S, H2SC, H2TE, H2PO. We have taken. Now, how the bond dissociation energy we have discussed. Now we will go for a bond dissociation energy for water. How much we said? 463 kilojoule per mole. 463 kilojoule per mole. Down the group, we said bond dissociation energy decreases. Bond dissociation energy decreases. Therefore, thermal stability. Bond dissociation energy decreases means easily dissociating. Therefore, thermal stability decreases. Thermal stability decreases in the sense they are giving hydrogen easily. Therefore, reducing nature increases. Reducing nature increases, you can say. Down the group, bond dissociation energy decreases. That means easily dissociating. So stability decreases. But easily dissociating means easily giving hydrogen for reduction. Therefore, reducing nature increases. Then we will see acid dissociation constant. Water dissociates to give H plus and OH minus. For this acid dissociation constant is a 1.8 into 10 to the power of minus 16. Then H2S dissociating to give H plus and HS minus. For this dissociation constant is 1.3 into 10 to the power of minus 7. So for H2SC, acid dissociation constant is 1.3 into 10 power minus 4. For H2TE acid dissociation constant is 2.3 into 10 power minus 3. So down the group, if you see down the group, Ka value increases. Therefore, acidic nature increases. That means why acidic nature increases? That means tendency to give H plus increases. That's why H2S is having more tendency to donate H plus than water, because bond dissociation energy of H2S is less when compared to water. So bond dissociation energy down the group decreases. Therefore, H plus donating tendency increases. So acidic nature increases. The experimental evidence is Ka increases. Therefore, down the group, we can say acidic nature increases. Okay. So to say acidic nature, we have to use bond dissociation energy in which case? In the sense for hydrates. For hydrates, oxygen family hydrates, halogen family hydrates, down the group bond dissociation energy decreases, acidic nature increases, we have to say. Okay, so seventh group hydrates, oxygen family hydrates. For that case, acidic nature we are explaining using bond dissociation energy, but not using electronegativity. If you use electronegativity, you will get opposite reasoning, you will get opposite answer, you will get. That will be against experimental fact. So don't use electronegativity. Why? Because electronegativity of oxygen is high, electronegativity of sulfur is low. Therefore, water should have high tendency to donate H plus than H2S as per electronegativity. So don't use electronegativity word for explaining this acidic nature. Use bond dissociation energy. So oxygen family hydrates and halogen family hydrates, acidic nature we can explain using bond dissociation energy, but not electronegativity. Next, we will take in the oxygen family hydrates, water alone liquid, rest or gas. In the oxygen family hydrates, water alone existing in liquid state, remaining or existing in gaseous state at room temperature. Because in water, intermolecular force is hydrogen bonding. In H2S, intermolecular force is not hydrogen bonding, van der Waals force. Therefore, then in this oxygen family hydrates, water is not acting as a reducing agent, but rest are acting as reducing agent. These are acting as a reducing agent, but water is not acting as a reducing agent, because this SH bond is having reducing nature, but in water, OH bond is having acidic nature. Therefore, in these are acting as these are having reducing nature, but water is not having reducing nature. So, in the oxygen family hydrates, except water, remaining all have reducing nature. Reducing nature, we can say reducing property. It is there, but this OH is not having reducing property. We are saying acidic nature. We are saying, but if you see acidic nature, water is having least acidic nature when in this group. In this group, which is having least acidic nature means water. So acidic nature down the group increases. Reducing nature also down the group increases. So water has least reducing nature. So rest of the compounds having higher reducing nature. Next, we will take oxides. We will take. Next, we are going for oxides. We will take oxides. We will take. Now, 6A group elements form two types of oxides. One is dioxide, another one is trioxide. 6A group elements form two types of oxides. One is dioxide, another one is trioxide. Now, we will take sulfur dioxide, selenium dioxide, tellurium dioxide, like this we have taken. And the trioxide, if you see sulfur trioxide, selenium trioxide, tellurium trioxide, we have taken. Now, how the acidic nature will be there, that we will see. If we go like this, acidic nature increases because SO2 with water gives H2SO3, SO3 with water gives H2SO4. Here acidic strength, if you see, here acidic strength is more, here acidic strength is less. Acidic strength is less. Therefore, SO3 is having more acidic nature when compared to SO2. What is the reason? When sulfur is having +4 oxidation number, here sulfur is having +6 oxidation number. If we go like this, oxidation number increases, therefore acidic nature increases, we can say. Now down the group you will see how the acidic nature is there. Down the group, acidic nature, how it is there, that is decreasing. Acidic nature decreasing. That means SO3 gives H2SO4. SeO3 with water gives H2SeO4. Now SO3 and SeO3, if you see, which is having higher acidic nature, means sulfuric acid is having higher acidic nature when compared to H2SeO4. Therefore, down the group, what happens means acidic nature decreases. Now, acidic nature decreases, that we can explain based on what, in the sense central atom electronegativity. Central atom electronegativity decreases. Central atom electronegativity decreases down the group. Therefore, down the group, acidic nature decreases, we can say. Sir, central atom electronegativity and acidic nature, what is the relation? That we will see. We will take sulfuric acid. We will take sulfuric acid, and selenic acid. We will take. We are taking selenic acid. We are taking selenic acid. Now, sulfur and selenium both are having same oxidation number here. Now, this is having high electronegativity. It is having low electronegativity. High electronegativity, therefore, bond is moving more tendency towards sulfur. Selenium, here bond is moving less tendency towards selenium. Therefore, this bond is moving with more tendency towards oxygen. This bond is moving with towards less tendency towards oxygen. Therefore, it is giving H plus easily, whereas it is not giving H plus easily. Therefore, this acidic nature is more, this acidic nature is less. Okay. So down the group, acidic nature decreases. It is oxy acids. In the oxy acids, down the group, acidic nature decreases. This we are explaining using electronegativity of central atom. But just before we have discussed oxides, this oxygen family hydrates. Down the group, what happens? Acidic nature increases. This acidic nature we are explaining using what? Bond dissociation energy, but not electronegativity. Using bond dissociation energy only we are explaining. So down the group of hydrates, acidic nature increases because bond dissociation energy decreases. Down the group of oxy acids, acidic nature decreases because electronegativity electronegativity decreases. Using electronegativity, we are explaining. So in the oxides, acidic nature decreases down the group. In the hydrates, down the group, acidic nature increases. Okay. So hydrates, down the group, acidic nature increases. In the oxides, down the group, acidic nature decreases. Here we are explaining using electronegativity. In the hydrates, we are explaining using bond dissociation energy. Sir. Next, we will see reducing nature. Now, out of SO2 and SO3, which will act as a reducing agent means SO2 but not SO3. Why? Because sulfur is in highest oxidation number. It cannot undergo oxidation still more. But this sulfur can undergo oxidation. Okay. Therefore, these dioxides are having reducing nature. Down the group, how the reducing nature is there, that we will see. Down the group, reducing nature, what happens? Down the group, reducing nature, what happens means it decreases. That means which is having higher reducing nature tendency. This SO2 reducing nature tendency will be more. TeO2 reducing nature tendency is less because of inert pair effect. Down the group, inert pair effect tendency increases. Down the group, inert pair effect tendency increases. Therefore, reducing nature decreases, we can say. Reducing nature decreases, we are saying. Okay. Let us go to next one. Now we will take sulfur dioxide gas. For this structure, we will see sulfur and 2 oxygens we will write. Sulfur belongs to 6th A group, therefore its valence shell contains 6 electrons. These 2 electrons going for double bond, these 2 electrons going for double bond. Now this sulfur, in this sulfur, 2 sigma bonds present, 1 lone pair is present. Therefore totally 3 electron pairs. 3 electron pairs, 1 you give to S, remaining 2 you give to P. Therefore sp2 hybridization. So sigma bond is formed by sulfur sp2 oxygen P. Here also sigma bond is formed by sulfur sp2 oxygen P. Then we will see regarding pi bond. Okay, regarding pi bond. Regarding pi bond, in the sense sulfur is having 3 p orbitals in the valence shell. Out of 3, 2 p orbitals it is giving for intermixing for hybridization. Remaining 1 p orbital is that p orbital it is giving for pi bond. Therefore p pi bond. Pi bond is p pi. Oxygen is giving p orbital. Next, sulfur is giving. Okay, it was having 3 p orbitals in its valence shell. Out of 3 p orbitals, 2 p orbitals have gone for hybridization. 1 p orbital have gone for this pi bond. So for this pi bond, this sulfur can give only d orbital. This oxygen can give p orbital. Therefore, it is d pi p pi bond, we can say. Okay. Next, SO3 gas we will take. That structure we will say. SO3 central atom is sulfur, surrounding atoms oxygen atoms. In the sulfur valence shell, 6 electrons present because it is 6th group. This valence shell is having 6 electrons. Each sulfur is making double bond with each oxygen. Okay. Here we will see hybridization. We will see this sulfur is having 3 sigma bonds. Therefore, hybridization what means sp2. 1 S, 2 P, totally 3. So 3. Pi bonds don't consider for saying hybridization. Here, in this sulfur, this valence shell is having 3 p orbitals. Out of 3, 2 have gone for hybridization. Remaining one is that one it is giving for pi bonding. Oxygen will give always p orbital for pi bonding. Then sulfur gives a d orbital for pi bonding here. Here also d orbital for pi bonding. Okay. So this sulfur gives d orbital for pi bonding. Here also d orbital for pi bonding. Here p orbital for pi bonding. So in this SO3, 1 p pi, 2 d pi p pi is there. Okay. Now SO3 in solid we will take. SO3 in the solid we will take. Here SO3 is in gas. Now solid we will see. SO3 in solid will exist in the form of, one is cyclic form, another one is chain form. Cyclic form we will see. In the cyclic form, SO3 will take. SO3 we will write like this. SO1 SO3. Another SO3 we are writing. Another SO3. Next SO3 we will write. Next SO3. Now 3 SO3 we have written. Now we will write, we will shift this pi bond between this oxygen and sulfur. This pi bond will shift between this oxygen and sulfur. This pi bond we are shifting between oxygen and sulfur. We are getting what, in the sense cyclic form we are getting. How that cyclic form will be there, we'll see. Now oxygen, sulfur, oxygen, sulfur, oxygen, sulfur, oxygen. This sulfur is having two double bond O's, two oxygens with a double bond. So it is a what in the sense cyclic form. This cyclic form is called alpha form. For this alpha form formula is S3O9 because in this one 3 sulfur atoms are there and 9 oxygen atoms are there. Therefore S3O9 is the cyclic form of cyclic alpha form of SO3 in solid state. Then we will see SO3 in solid state in chain form. We will see SO3 in solid state we will take. Now I will write one SO3 like this. Next SO3 I am writing. Next SO3. Next SO3 I will write. Next SO3 like this I will write. Now we are discussing about what in the sense chain form. This pi bond is coming in between oxygen and this sulfur. This pi bond is coming in between oxygen and sulfur. This pi bond is coming in between oxygen and next sulfur. Here one pi bond comes with this sulfur. Okay, so we can write this as what in the sense. This how to write this structure we will see. So this structure we can write here. Here one oxygen will be there. Here also one oxygen will be there. Here it continues. Here it continues. This is called a chain form. We can say this chain form we can say as a beta comma gamma form. Chain form beta comma gamma we said. Next we'll discuss about halides. Oxygen family halides we will discuss. This oxygen family elements form halides of which type in the sense one is a dihalide, one is a dihalide, next one is a tetrahalide, next one is tetrahalide, next one is pentahalide. Okay, it is in general. Particular element if you see in these possible, in addition other halides also possible. Now we will take hexahalides. We are taking hexahalides. How these hexahalides are possible that we will see. This hexahalides. In the hexahalides, hexafluorides are stable. Hexafluorides are stable. Other hexahalides are unstable. Other hexahalides are unstable, we can say. Why other hexahalides are unstable? Because size of surrounding atom increases, therefore stability decreases. That's why unstable. Said. Next, we'll see all the hexahalides exist in which physical state in the sense gaseous state. All the hexahalides exist in gaseous state we are saying. Said. In the hexafluorides, SF6 is in the hexafluorides, SF6 is having very high stability. SF6 is having very high stability. Therefore, SF6 is not undergoing hydrolysis. Whereas TEF6 is undergoing hydrolysis. TEF6 is undergoing hydrolysis. SEF6, the SF6 is not undergoing hydrolysis. Why SF6 is not undergoing hydrolysis? That we'll see. First, we will see hydrolysis means what. Hydrolysis means, suppose TEF6 is undergoing hydrolysis. That hydrolysis, how it will be there, that we will see. Here TEF6 octahedral we will give octahedral structure. Now water molecule is coming. Water molecule is having lone pair. Therefore, what happens means this oxygen is donating lone pair, contributing lone pair to this tellurium. So what we are getting in the sense, we are getting like this. We are getting like this. Here positive, here formal charges will give, here minus will give. Okay. Next step what happens means here formal charges plus. Next step what happens in the sense this bond is migrating, this bond is migrating. Therefore HF is leaving. HF is leaving. That means in the place of F, what is there means OH is there. Okay. Now SF6 is not undergoing hydrolysis. Why? Because one point is S bond F. This bond strength is high. Therefore, breaking of this bond is not easy. Then in SF6, sulfur is not going for 7 coordination. Here see 7 bonds are there. Sulfur is unable to go for 7 coordination. In the 6 coordination itself, it is getting saturated. So sulfur covalence is 6. 7 coordination it is not going, whereas tellurium going for 7 coordination. Therefore, hydrolysis is possible. And If water comes, steric hindrance around sulfur is getting high. Therefore, SF6 is not undergoing hydrolysis. So why SF6 is not undergoing hydrolysis? One reason is this SF bond strength is high. Next one is sulfur is unable to go for seventh bonding. Seventh bonding. So it is having coordinative saturation. Therefore, it is not going for seventh bonding. Then, due to attack of water, steric hindrance in SF6 is getting high. Therefore, SF6 is not undergoing hydrolysis. It is having what in the sense low reactivity. Next, oxygen is not forming hexafluoride. Oxygen is not forming hexahalide. Oxygen is not forming tetrahalide. Why? Because in oxygen coming under second period, its valence shell is second shell. In the second shell, 2s2p is there. There is no more vacant orbitals. Therefore, it is unable to form 6 covalency or 4 covalency. Okay. Then, so regarding hexahalides, so on so points we have discussed. Now we will go for tetrahalides. Tetrahalides points we will discuss. SF4. SF4 is gas. SF4 is gas. SCF4 is liquid. SCF4 is liquid. TEF4 is what in the sense solid. TEF4 is solid. Okay. These are having what geometry in the sense seesaw geometry they are having. Okay. Next we will take dihalides. We will take. We are taking what in the sense dihalides. In the dihalides, selenium is not forming dihalides. Selenium in the oxygen family, selenium is not forming dihalides. Rest of the elements are forming dihalides. What are the dihalides in the sense of dichlorides and dibromides they are forming? Then diiodides are not possible. Diiodides are not possible. Then dihalides are not having stability. Dihalides are not having stability, we can say. Next, we will go for monohalides. We are going for monohalides. For example, sulfur monohalide means SF. Here, in this case, this monohalides, this SF is not existing like this. Why it is not existing like this in the sense sulfur belongs to 6th group, therefore its valence shell contains 6 electrons. Out of 6 electrons, 1 electron has gone for bonding with fluorine. This electron is lone electron, separate electron, isolated electron. Therefore, it is going for dimeric. In the dimeric form, if you see, sulfur is not having unpaired electron. Sulfur, you see, it is not having unpaired electron. Therefore, it is in the monohalide is going for dimerization. Sulfur monofluoride, we can write it as S2F2. Sulfur monochloride, S2Cl2. Sulfur monobromide, S2Br2. Selenium dichloride, Se2Cl2. Selenium dibromide, Se2Br2. Like this monohalides we can see. Now, these dimeric halides undergo disproportionation. Dimeric halides can undergo disproportionation. Se2Cl2 can undergo disproportionation to give what in the sense SeCl4, SeCl4 and silicon like this. And selenium, this Se is called selenium. So this monohalide Se2Cl2 monohalide undergoes disproportionation to give here +1, here +4, here 0. It is undergoing disproportionation to give selenium tetrachloride and selenium we can say. This is about dimeric halides. So dimeric halides, what we are saying means it is undergoing disproportionation. Next we will see preparation of oxygen. Preparation of oxygen we will see potassium chlorate. Chlorate salt. Chlorate salt on heating decomposes to give oxygen. Chlorate salt on heating decomposes to give oxygen. Then nitrate salt. Nitrate salt. Nitrate salt on heating gives oxygen gas. Next we will see chlorate salt. We have seen nitrate. We have seen permanganate. Permanganate on heating gives O2 gas. Permanganate on heating gives oxygen gas. Okay. Next one is what in the sense thermal decomposition of metal oxides. Some metal oxides on thermal decomposition gives metal and oxygen. Which one in the sense silver oxide? Silver oxide is easily decomposing to give silver and oxygen. Mercuric oxide easily decomposing to give mercury and oxygen. Sorry. Lead dioxide undergoes disproportionation to give lead monoxide and oxygen. Lead dioxide on disproportionation gives lead oxide and oxygen, lead monoxide and oxygen. Then hydrogen peroxide easily decomposes to give water and oxygen. That's why hydrogen peroxide is stored in plastic bottle in order to suppress its dissociation. Then we'll see electrolysis of water gives oxygen gas. Distillation of air. Distillation of air gives oxygen gas. Then we'll see properties of oxygen gas. There is no color for oxygen, no smell. Solubility of oxygen in water is low. Oxygen is paramagnetic due to two unpaired electrons. Then metals like arsenic, platinum, and noble metals and noble gases do not react with oxygen under normal condition. Okay. What is the uses of oxygen? It is used for respiration, for combustion, oxyacetylene welding, manufacture of metals. Okay. Next we will see about ozone. Next we are seeing about ozone. Now we will take oxygen gas. Oxygen gas will pass through silent electric discharge. We are taking oxygen gas. We are passing through silent electric discharge. What we are getting in the sense ozone we are getting. Oxygen gas on passing through silent electric discharge, we are getting ozone. We are saying. Okay. So here what is silent electric discharge? In the sense high voltage you have to give, but heat will not be produced. The temperature, low temperature only will be produced. Okay. That is called silent electric discharge. Now here produced ozone is called ozonized oxygen. This produced ozone is called ozonized oxygen. Why we have to call ozonized oxygen? Means in this one 10% ozone only is there. 10% ozone only is there. Remaining are what? In the sense oxygen. Okay. Next properties of ozone we'll see. Properties of ozone. Pure ozone is a pale blue gas. Pure ozone is pale blue gas. Dark blue liquid, violet black solid. That means ozone physical state is different, means color also different. Ozone when it is in gaseous state pale blue, when it is in liquid state blue liquid, when it is in solid state violet black solid we can say. Then this ozone, small concentrations of ozone is not affecting us, but higher concentration of ozone is causing headache and nausea. So higher concentration of ozone is dangerous to us, and high concentration of ozone is dangerously explosive. High concentration of ozone is dangerously explosive. Why is it so? That we'll see. Now we are taking ozone. This ozone is vapor. It is converting into oxygen vapor. Let us balance this one like this. Ozone on decomposition gives what? In the sense oxygen gas. For this reaction delta H is equal to negative. For this reaction delta S is equal to positive. Why positive? In the sense here 3 moles, here 2 moles. Both are gases only. 2 moles converting into 3 moles means delta S is positive, we have to say. Then delta G we will see. If both are, it is favorable for the process, it is also favorable for the process. If both are possible, then we can substitute like this formula. Delta G is equal to delta H minus T delta S formula we can say. In this delta G is equal to what? In the sense negative. Delta H is favorable, delta S is favorable, delta G also favorable for this process. Therefore, this ozone, high concentration of ozone is dangerously explosive. We are saying. Okay. Next, ozone acts as powerful oxidizing agent. Ozone acts as powerful oxidizing agent. It is converting what into what? That we will see. It is converting PbS plus ozone gives PbSO4. PbS with ozone gives PbSO4. What is the mechanism involved in this one? That we will see. Now we can say that here PbS reacting with ozone to give what in the sense PbSO4, we can say PbSO4 is white, PbS is black. Now if we see, due to pollution, if anything becomes black, then that can be washed away. How? In the sense, we will take statue, we will take. On leaving for several days, it is converting, this statue surface is becoming PbS. Therefore, it is black. To this, what is passed in the sense ozone, it is converting into PbSO4, which is white. So, to convert PbS black color into PbSO4 white, we can use what in the sense ozone we can use. Okay, next reaction we'll see. I minus with ozone plus water. I minus with ozone plus water gives what means I minus is converting into I2, water is converting into ozone. Next, stannous chloride will take SnCl2. Stannous chloride plus ozone gives stannic chloride. Stannic chloride we can say. So stannous chloride with ozone gives a stannic chloride. So now ozone is a powerful oxidizing agent in comparison to oxygen. Why? Because ozone can decompose easily when compared to oxygen. So in the oxidizing nature of ozone, what are the equations we have discussed in the sense PbS becomes PbSO4, ozone becomes oxygen gas. Next, I minus becomes I2, mercury becomes a mercurous oxide. This mercurous oxide case, if mercury is converting into mercurous oxide, its meniscus will be lost. Mercury will have meniscus at the surface. If mercury is becoming mercurous oxide, the meniscus is lost. Then it is sticking to glass. Whereas mercury is not sticking to glass. Mercurous oxide is sticking to glass. Therefore, better to use ozone, and this ozone is doing like this. Due to ozone, mercury is converting into mercurous oxide. Mercurous oxide is used as cunning agent. Mercurous oxide is having meniscus. Due to meniscus in the surface, this mercury I will take, it is having meniscus in the surface. Mercurous oxide, no meniscus. This mercury is not sticking into the glass. It is sticking into the glass. That means the nature of mercury is changing because of mercurous oxide. This property is called tailing of mercury. This property is called tailing of mercury, we can say. Next, how to estimate ozone practically? That we'll see. Now we will treat ozone in this manner. We will take ozone for this chemical reaction. This iodine we will titrate with hypo solution. This iodine we will titrate with hypo solution. What we are getting means Na2S4O6 and sodium iodide we are getting. So based on this titration, that means pipette solution, burette solution titration, we can find a number of moles of iodine liberated. From number of moles of iodine, we can say number of moles of ozone. From this, we can estimate ozone. That means what is the amount of ozone present that we can estimate. Next, depletion of ozone layer due to supersonic jets. They are exerting nitric oxide, supersonic jets. From that exhaust, nitric oxide will be there. That nitric oxide depletes ozone layer. Then in refrigerator we are using freons. That freons depleting ozone layer. Okay. Next we will see ozone resonance structure. We'll see ozone contains 3 oxygen atoms. That 3 oxygen atoms we have written like this, like a bent form, and each oxygen is having 6 electrons in its valence shell. That 6 electrons we will write. For this oxygen also 6 electrons. For this oxygen also 6 electrons. Okay, here what happens means, here now we will go for bonding between these two oxygen. Double bond is there. This oxygen can make, this oxygen is having only 2 unpaired electrons. Therefore it can make two normal covalent bonds. So it can make the two covalent bonds. It can make. This valence shell is not having any vacant orbital. Therefore it will contribute this lone pair for dative bonding. This oxygen is having only 2 unpaired electrons in the valence shell. Valence shell is not having any other vacant orbitals. Therefore it can make 2 normal covalent bonds. Okay, another bond in the sense a dative bond only possible. Okay, sir, now we will write a resonance. That means this dative bond we will write it as normal covalent bond by giving formal charge, here +1, here -1. Okay, so now resonance structure will write for this. Then we will go for resonance hybrid. Resonance hybrid means what you have to do means, here single bond, here single bond you have given. This pi bond we will distribute off into here, off into here. This -1 we will distribute minus of here, minus of here. Then lone pair will be there. Then plus charge will be there. This is called a resonance hybrid of ozone. Resonance hybrid of ozone, like this you are seeing. Next, what are the uses of ozone? It is used as a germicide in order to kill germs. How it is used as a germicide? How it is used as a germicide, we'll see. This ozone decomposes to give O2 and nascent oxygen. This nascent oxygen kills germs. It is used as disinfectant. It kills. It is used as a disinfectant. Then it is sterilizing water. So in the RO water, in the drinking water bottles, if you see, ozonized water will be written, because ozone is used for sterilization, because it is acting as a germicide and insecticide. Therefore it is used for sterilizing water. Okay, next, ozone is used as a bleaching agent. Bleaching agent means unwanted color will be converted into colorless. Unwanted color will be converted into colorless. So unwanted color, to that you add ozone, that unwanted color becomes colorless. Therefore ozone is used as bleaching agent. Then ozone is acting as a oxidizing agent. Then ozone is having permanent dipole. It is a dipolar molecule. Actually ozone is a element. All the atoms are similar, but even then it is having permanent, that means dipole moment we cannot say. Why? Because why we cannot say dipole moment? In the sense all the atoms are same atoms, so electronegativity is same. Electronegativity is same in the sense, how to say dipole moment? So we cannot say dipole moment. Okay, this ozone is showing bleaching action. This bleaching action is permanent. Why? Because why we will say this ozone is giving nascent oxygen. This unwanted color becomes colorless with this nascent oxygen. Okay, with this nascent oxygen, this unwanted color becomes colorless. It is oxidized one. It is oxidized one. It is exposed to atmospheric air, means it will not undergo further oxidation because it is already oxidized. Therefore it is not undergoing oxidation with atmospheric air. Therefore bleaching by ozone is a permanent process, we can say. Okay, why? Because ozone bleaching is oxidation. Ozone is giving nascent oxygen. This nascent oxygen removes unwanted color. That means it converts unwanted color into colorless. It is oxidized one. Therefore it is not converting into any other with atmospheric air. Okay, so this is about ozone, we can say. So in the ozone, this chemical reaction will see PbS plus nascent oxygen gives PbSO4. This chemical reaction, ozone gives nascent oxygen. This nascent oxygen converts PbS into PbSO4. Here we need 4 nascent oxygen. So multiply this with 4. So we will get what? In the sense PbS plus 4 ozone